So second part of week 2, we're talking about section 2.2, which is about the inverse of a square matrix. Week 2 in general is about matrices, doing Gaussian elimination on them, reducer echelon form, systems of equations. They all kind of interface with the idea of the inverse of a square matrices too. So that's what 2.2 is about. So the inverse of a matrix is a very important property / function of a matrix, which tells us a lot about the system as well, and is very useful for us for when we're trying to solve for information about a matrix. For matrices, only square matrices can even have an inverse. You can't have the inverse of a non-square matrix. Further, not all square matrices have an inverse. An inverse is equivalent to, for scalars, just like division. So when we have matrices, we have matrix multiplication, but there's no way to kind of divide by a matrix. So multiplying by the inverse is kind of similar to for scalars, where we multiply by the reciprocal when we want to remove something. So we can do the same thing with an inverse. If we want to cancel out something, we can multiply it by its inverse. So for the first thing, we're saying in order to solve our system ax equals b, we can isolate x by multiplying both sides of the equation by the inverse a to the negative 1, such that x equals a to the inverse b. So ax equals b, usually if I wanted to solve for a, if this was just an equation, I would just divide by a, right? And then I get x is equal to b over a. I can't do that with matrices. So here I'm going to multiply by the inverse. So ax equals b, I can multiply on the left, on both sides, by the inverse, giving me these cancel out, and then I'm left with x is equal to a inverse b. That's an application of the inverse. We'll have many other applications of the inverse. That's just one thing we can use it for. Again, like I said, not all square matrices have inverses. So the property of having an inverse is something called invertibility. So the inverse of a matrix exists if and only if. So again, it doesn't always happen, is if the matrix is square, like we said, and that it has full rank is what we consider. So if it's an n by n and the rank is n, we consider that matrix having a full rank, and it will be invertible. If the rank is less than n for a square matrix, it will not have an inverse. We cannot solve for the inverse of the matrix. This is a property where a times its inverse is equal to its inverse times a is equal to the identity matrix. Again, this kind of goes along the lines of the idea of it being like division or the reciprocal of something. So if you had a number, let's say the number is 5 times its reciprocal is equal to itself times its reciprocal is equal to 1, right? Same thing here, but the biggest thing that we want to note is that for numbers like the reciprocal, it's normal that the order doesn't matter. But here, like we said earlier, matrix multiplication order does matter. However, for an inverse, if you're multiplying something by its inverse, the order doesn't matter, because no matter what, it's going to equal the identity matrix. To compute the inverse of a matrix, we're going to take the matrix, augment it, recall that, with the entire identity matrix. So previously we've only augmented with vectors, but this case we're going to augment with an entire matrix, and then row reduce that matrix until we get that the right-hand side is the identity. So the left-hand side. We row reduce until we get the reducer echelon form of A to B, the identity matrix. Then whatever we did to the identity matrix originally is now going to be the inverse. Some terms, invertible means that it's non-singular. So if something has an inverse, it's invertible and it's called non-singular, and something is non-invertible, so it doesn't have an inverse, it's called singular. You don't really need to know that, but it might just come up in a problem, so it's just easy to hear beforehand. And here are some properties of inverses. So inverses are the calculation of inverse is involutive, which is the same thing as a transpose. It's just a general term where if you do something twice, it undoes it. So if you divide by, if you do the reciprocal of something twice, it'll go back to the original number. Same thing with the inverse. If you invert something, invert it again, you're going to get the original thing. If you have a product A, B, and you take the inverse of that, that is equal to the individual inverses, but the order must be flipped. Again, order matters. And then if you were to take the transpose and the inverse, the order in which you do those two operations don't matter. So if you take the transpose and you take the inverse, or if you take the inverse then you take the transpose, you'll get the same result. For a 2 by 2 matrix, we don't have to do this whole process, which is great because this process, as we will see, sucks. For a 2x2 matrix, we have this formula that we can use where for any matrix, so A, B, C, D, the inverse of that matrix is just this calculation. So we do 1 over AD minus BC, and then we flip A and D, and then we negate B and C. That's it. Do not ever do this process to solve for the 2x2 inverse. Always use this. It's going to save you so much time. And yeah, just don't memorize this. It's going to help you in the future a lot. So that's kind of the idea of matrices. Let's do an example. So this is the matrix that we used in 2.1 for solving for the reduced echelon form. So we're going to do the same thing, so follow the same steps, so it should be quicker. But this time we're solving for the inverse. So we are going to augment A with I. Is our first step. The matrix is 5, 10, 5, 3, 12, -9, 4, -4, 12. And when you're given a matrix and you're asked to solve for the identity matrix or the inverse of it, you don't necessarily know if it is invertible or not. There is nothing like super fast you can do. We'll talk about how concepts are related that we can determine invertibility, but if something asks you to solve for the inverse, you could go about it and be like, oh my gosh, I can't get the reduced echelon form to be the identity matrix. It might not be invertible. It might just not have an inverse, and that's the end of it. So for this one, we're going to do the same steps that we did previously, so we can go a little bit quicker. So whatever I'm going to do to the left-hand side, I have to do to the right-hand side too. So the rows that don't change, 0, 1, 0, 4, -4, 12, 0, 0, 1, 1, 2, 1, 1/5, 0, 0. So just making sure that you don't miss any parts when you end up doing it on the left-hand side. You must do it also to the right-hand side. So row 2 is equal to 1, row 2 minus 3, row 1, row 3 is equal to row 3 minus 4, row 1. Row 1 stays the same, 1/5, 0, 0. These become zeros, 12. We got 6, -12. This 0 is now going to become -3/5. This is going to stay 1, 0, 0, -12, 8. This is now going to become -4/5, 0, 1. So doing the same operations we did before. Next thing is I want to get rid of this -12 in the bottom. So I'm out of space. So I'm going to keep going. Getting rid of this -12 on the bottom. R3 is equal to R3 plus 2 R2. 2, 1. 1/5, 0, 0, 0, 6, -12, -3/5, 1, 0. And this one is changing. I didn't color code these for changing earlier. Okay. 0, this goes to 0, 8 plus -24 is -16. And then this -4/5 becomes -2. This is going to become 2 and 1. So this is essentially the same thing as doing reduced echelon form, but just making sure every operation that you do on the left-hand side also applies to what you're doing on the right-hand side. 6, -12, -3, 1, 0. 0, 1, 1/8, -1/8, 1/16. Now I want to get rid of this -12 up here, so I'm going to do 2 is equal to row 2 plus 12 row 3. Row 2 is changing, so I'm going to keep row 3 and row 1 the same. 0, 6, 0. And then the negative, this becomes 9/10, -1/2, -3/4. Carrying on. I'm going to turn the 6 into a 1, so row 2 is equal to 1/6 row 2. 1, 2, 1. 1/5, 0, 0, 0, 0, 1, 1/8, -1/8, 1/16. Then just dividing everything by 6. 0, 1, 0. That's going to become 3/20, -1/12, and -1/8. Almost there. Obviously, I'm looking at an answer key that I wrote for this, but you can imagine how long these computations would be for something that's has a lot of fractions in it, has a lot of steps in it. So it's just really important to be very meticulous in how you're solving for these and just being really careful. Because if you can't tell, it's very easy to mess this up and just forgetting to do one singular operation on the right-hand side would completely ruin your answer. So, like I've said, make sure you show your work and show every step that you're taking to get there. So row 1 is equal to row 1 minus row 3. So 1, 2, 0. 1/5 minus 1/8 is 3/40. And then I've got positive 1/8. And then, did I drop it somewhere? Oh no. See, I'm literally looking at the answer and I messed this up. This should be negative. This is 1/16. And then lastly, we want to get rid of this 2 up here. So I'm going to do one last row operation where row 1 is equal to row 1 minus 2 row 2. Keeping row 2 and row 3 the same. One, 0, 0, and then subtracting that gives us -9/40, 7/24, and 5/16. And that is, so we look at this, we see that the left-hand side became the identity matrix, so the reduced row echelon form of A being the identity matrix means that A is invertible, and the inverse of A is this. Looking at this, it's a really gross matrix, I would say. It has a lot of fractions, it's really ugly, has a lot of negatives. The matrices that you will probably get when you solve for them are not going to be this gross, but it kind of shows you how meticulous you need to be to solve for the inverses of these matrices. And a lot of the times, it might ask you to solve for the inverse, but if it just asks you, does the inverse exist? You just have to get to the point where you understand that the reduced row echelon form is the identity matrix. Once you establish 3 pivot variables, you will, in a 3x3, you know that that's going to be true for a rank of n. So when it has 3 pivot variables for a 3x3, that means there's no free variables. So we have that unique solution. So we have the identity that's the reduced row echelon form, that's the identity. As you can see, a lot of these concepts insist upon each other and they tell each other these things, which we'll talk about in a few weeks, how they're all related. But yeah, so everything is related for these inverses. So that's how you calculate the inverse of a 3x3. or and beyond, right? So there's no such thing as an inverse of a 1 by 1. The inverse of a 2 by 2 is using this formula. And then for 3 by 3 or 4 by 4 or beyond, you always have to just augment it with the identity matrix and solve for the reduced echelon form. Cool. So now just to discuss the worksheet questions. So the first question is, let A be a square n by n matrix. We don't know what size it is, just n by n. Let B and C be other n by n matrices such that BA is equal to I equal to AC. Prove then that B is equal to C. We can't just be like that this is like obviously true, because we could have that some things are like the zero matrix and stuff. But the easiest way that we can go about this is just saying that let's start with B, because we're going kind of from B to C here. B is equal to B times the identity matrix. That's what the definition of the identity matrix is it is associative, right? So whenever you multiply a matrix by its associated identity matrix, it is still itself. We are told that I is equal to AC, so I can do B is equal to AC, or B times AC. This is the same thing. And matrix, it is not commutative, but you can redistribute the parentheses. So we can change this to BA, C, and then we know that BA is equal to the identity matrix. So I is equal to BA. So this is IC, which is then just equal to C, proving that B is equal to C by using the identity matrix properties and going through there. Okay. Last question for 2.2 and inverses. We'll find the 2 by 2 matrix A that satisfies the following matrix equalities. So here we're told, so A is a 2 by 2 matrix so this is a 2 by 2, this is a 2 by 1, this is a 2 by 1, this is a 2 by 2, this is a 2 by 1, this is a 2 by 1. So there's some matrix A that's a 2 by 2 that is true with these two expressions. So these two systems of equations is solved by some matrix A. Combine the two given equalities into one, A, B equals C, where B and C are 2 by 2 matrices. So they're telling us kind of to condense this all into one thing, which is pretty straightforward, because we can just do that A is equal to 1, 1, 1, 2 is equal to 3, 7, 5, 11. That's just how it works out, because think about how you go row times column is equal to some values, and then row times column is some values. So these are able to be combined in that way. This is A, this is B, and this is C. Use the formula from the lecture. Lecture is just math 240 lecture. Compute the inverse. So they're asking us to use the formula for A inverse of a 2 by 2 to compute B inverse. So the inverse of B for given some B is going to be 1 over AD minus BC. We switch D and A, and we negate B and C. So B, we just formed, is 1, 1, 1, 2. 1, 1, 1, 2. So the inverse of it is going to be where we have 1 over AD, so 1A times D minus B times C, multiplied, switch A and D, so 2, 1, and then negate B and C, negative 1, negative 1. 1 over 2 minus 1 is just 1. So the entire thing, the inverse is just 2, negative 1, negative 1, 1. Multiply both sides of AB equals C by B, the inverse of B on the right, and perform matrix multiplication to find A. So we have AB is equal to C, and they want us to do AB and multiply by the inverse of B on the right in both cases. So on the right of both sides, and solve for A. So this cancels out, and then I'm left with A is equal to C times B inverse. So they want us to compute A explicitly because we know C and now we know B inverse. So C is this guy, 3, 5, 7, 11. 3, 5, 7, 11. And the B inverse is what we just computed. 2, negative 1, negative 1, 1. Inverse. I want to solve for A. Looking at this, I already knew A was a 2 by 2, but I can also see that it's going to be a 2 by 2 because these match, and it's going to result in a 2 by 2. So I can multiply these out. 3 times 2 plus 5 times negative 1, 3 times negative 1 plus 5 times 1, 7 times 2 plus 11 times negative 1, 7 times negative 1 plus 11 times 1. And I can do this out. 6 minus 5 is 1. Negative 3 plus 5 is 2. 14 minus 11 is 3. And then negative 7 plus 11 is 4. So this is my matrix A. It's just 1, 2, 3, 4. And that's it for inverses of square matrices. Again, this section was literally just dedicated to being able to solve for the inverse of a matrix. We're going to talk about how to use it, what it implies with the system, and all these other things later on, especially next week and the week after. So make sure you understand how to solve for it. And if you understand reduced root echelon form, then you should be fine, because it just comes down to doing reduced root echelon form augmented with the identity matrix. So yeah, that's the inverse of a square matrix.